Hi, we continue solving exercise sheet 6 and we will solve now exercise 6. We need to find the limits of these functions when x tends to 0 or plus infinity using the finite expansions. So the first function we have, it's exponential sine x minus square root of 1 plus 2x over cosine x minus chx. So as we learned from the course, to find the limit of the ratio we need to calculate the first non-zero term in the finite expansion of the numerator and the first non-zero term in the finite expansion of the denominator. So we start by, let's say, the denominator. So if we take cosine x minus chx, we start calculating the finite expansions of cosine and chx. Cosine will start by 1 and chx as well. So when we calculate the difference, this one will disappear, so we need to go further. If this one didn't disappear, so we don't need to go further because we need only the first non-zero term of the expansion. Then cosine x will continue by minus x2 over 2 and chx will continue by plus x2 over 2. This term will not disappear when we calculate the difference, so we can stop right there. So we can say that I will erase it to put it closer to each other. So we will say that I will calculate the finite expansion of cosine x to the order 2 plus x2 epsilon of x times 1 plus x2 over 2 plus x2 epsilon of x. This will be equal to 1 minus 1 is equal to 0, and then minus x2 over 2 minus x2 over 2 is equal to minus x2 and plus x2 epsilon of x. Now let's look at the numerator. We have exponential sine x from one side and square root of 1 plus 2x from the other side, and we have the difference of these two. Here it's tricky. It's not easy to find out which order we are gonna consider, so we have to write it down. Let's consider that we do to the order 2 or 3, for example. To start with, we'll say that it's exponential x minus x3 over 6 plus x3 epsilon of x. So it will be equal to 1 plus x minus x3 over 6 plus half x minus x3 over 6 to the power 2 plus 1 over 6 x minus x3 over 6 to the power 3 plus x3 epsilon of x. And for the so if we make the calculation, it will be 1 plus, we have x, and then we have plus x2 over 3 plus the x3 will disappear, so we have x3 epsilon of x. Now for the square root of 1 plus 2x, we have it's equal to 1 plus half 2x, now we are used to do it, plus half times half minus 1, because it's half times alpha minus 1 times 2x to the power of 2 plus 1 over 6 times half minus 1 times half minus 2 times 2x to the power of 3 plus x3 epsilon of x. So this will give 1 plus, we have 2x over 2, it's x, plus for the x2 we have minus 1 over 2x squared and plus x3 over 2 plus x3 epsilon of x. So now we can look at the difference. So if we calculate the difference, the 1 will vanish, the x will vanish, the x2 will not disappear, so we needed only the x2, we didn't need to go to the x3 term. So f of x, or the limit, will be the limit when x tends to 0 of f of x, if f of x is this. So the limit of f of x will be equal to the limit as x tends to 0 to the ratio of these two finite expansions. So in the numerator we have, if we make the difference between sine x and radical 1 plus 2x, we have x over 3 minus half x2, or x2 over 3 minus half x2. Excuse me, let me correct something here. This is x2 over 2 and not over 3. x2 over 2. So if we put x2 over 2 and then minus x2 over 2, it will be x2. So we'll have x2 plus x3 epsilon, or even x2 epsilon of x. We don't need to go to the third order, over minus x2 plus x2 epsilon of x. So if you take the first terms, the x2 over minus x2, the limit will be minus 1. So the limit will be minus 1 in here. Now we need to calculate the limit when x tends to plus infinity of e1 over x minus cosine 1 over x over 1 minus square root of 1 minus 1 over x squared. Now of course we want to transform this to the neighborhood of 0, so let u be equal to 1 over x, then f of x will be equal to a function g of u that will be equal to eu minus cosine u over 1 minus square root of 1 minus u squared. So this is the limit that we need to find, and the limit of f of x when x tends to plus infinity will be the limit of g of u when u tends to 0 of it's the limit of eu minus cosine u over 1 minus radical 1 minus u2. So again, we need the first non-zero terms in the expansions. So let's look at the denominator first. 1 minus square root of 1 minus u squared is equal to 1 minus, and then I will write the expansion of 1 minus u squared. It starts by 1, that will vanish with the other one, plus half u squared, and here I can stop because, sorry, it's minus u squared, and here I can stop because now I have one non-zero term in the expansion. So plus u squared epsilon of u, it's equal to half u squared plus u squared epsilon of u. Then if I take a look to the numerator, we have eu minus cosine u, which is equal to eu will start by 1 plus u, and cosine u will start by 1, that will vanish, minus u squared over 2. So now if you calculate the difference, you will have u that will remain in here. So you don't really need this u squared. So I will remove it. I will say it's plus 1 plus u epsilon u, and here it's 1 plus u epsilon u. Of course I should calculate both to the same order. Okay, that's for sure. But what is the order that we need? It's the order that will give us one non-zero term in the finite expansion. Then the limit as u tends to 0 of g of u is equal to the limit of u plus u epsilon of u in the numerator over half u squared plus u squared epsilon of u in the denominator when u tends to 0. And since the starting order in the denominator is higher than the starting order in the numerator, then the limit will be 1 over 0, which will be infinity. And here it's of course plus infinity because you have the coefficients like 1 and half in here. So it's equal to plus infinity. All we need to do is to take u as a common factor in the numerator and the denominator, and then simplify and then go to the limit, and you will obtain plus infinity. Now we need the limit of ln of 1 minus 2 sine x over sh to x at 0. So the same thing we'll do. sh to x is equal to 2x plus x epsilon x, and that's all, because we don't need to go further in the expansion. We need only the first non-zero term of the expansion. And then we go now for the numerator. It's a bit more complicated because it's 1 minus 2 sine x inside ln. So first 1 minus 2 sine x is equal to 1 minus 2 times the expansion of sine, which is 2x plus x3 plus etc. Maybe we will not need more than 2x, we'll try, plus x epsilon of x. So if we replace this in ln, it means that ln of 1 minus 2x plus x epsilon x, so which is the expansion to the first order. So we will obtain the first order for ln 1 plus u. In this case, the u will be this term in here, and then the expansion will be it's equal to first u, so minus 2x plus u squared and whatever, so u squared will be x squared. I will stop in here because I have a non-zero term, plus x epsilon of x. Then the limit of the function f of x will be, as x tends to 0, of course, the limit as x tends to 0 of minus 2x over plus x epsilon x, of course, over 2x plus x epsilon of x. And the first two terms are of order 1. Then I take the ratio of the coefficients, which will be equal to minus 1. And this is the limit. We move now to exercise 7. Consider the real function f of x. F of x is defined as x plus square root of x2 minus 1 for x belonging to minus infinity minus 1 union 1 plus infinity. Using the finite expansion in the neighborhood of plus or minus infinity of the function, prove that the curve has an oblique asymptote. So, even if I don't say that you will use the finite expansion in the neighborhood of plus minus infinity, when I say find the asymptote, you yourself will start using the finite expansion in the neighborhood of plus or minus infinity. So the first step that you do, immediately you say let t be equal to 1 over x, which will make t goes to 0 when x tends to plus or minus infinity. So I start by this, and then I modify the function, and I say then g of t will be equal to g of t being equal to f of x is equal to 1 over t plus square root of 1 over t squared minus 1. So always when I look for asymptotes, this is what I should do. I should replace x by 1 over t in the function and transform the function as a function of t and work in the neighborhood of 0. So again, this will be equal to, then g of t will be equal to 1 over t plus 1 over absolute value of t, if I take 1 over t squared as common factor inside the square root, times square root of 1 minus t squared. So this is the g of t that I have. Now I need to calculate the finite expansion of this function in the neighborhood of 0, or I will need to try to calculate finite expansion, but because we have a 1 over t term in here. So what I need to do is to calculate the finite expansion of this term in here. So I know that, we know that in the neighborhood of 0, square root of 1 minus t squared is equal to 1 minus u over 2, so it's t squared over 2 plus t squared epsilon of t. Now a little bit later I will tell you why I stopped at the standard order in here. So we take this and then we replace in the function, then g of t will be equal to, of course it's f of 1 over t, it's equal to 1 over t plus 1 over absolute value of t times 1 minus t squared over 2 plus t squared epsilon of t. Now we have two cases. If t goes to 0 plus, it means that x is going to plus infinity. This is the first case. Then g of t will be written as 1 over t plus 1 over t times 1 minus t squared over 2 plus t squared epsilon of t, which is equal to 2 over t minus t over 2 plus t epsilon of t. Then f of x is equal to 2x minus 1 over 2x plus 1 over x epsilon of 1 over x, and this is what we call the asymptotic expansion at plus infinity of f. And when we obtain this asymptotic expansion, we notice immediately that the limit of f of x as x tends to plus infinity minus 2x is equal to the limit as x tends to plus infinity of 1 over 2x or minus 1 over 2x plus 1 over x epsilon of 1 over x, which is equal to 0, then y equal 2x is an oblique asymptote of f at plus infinity. So you don't need to write this at each time, but I'm writing it in here to clarify the idea. So what you need to know is that when you calculate this asymptotic expansion in the neighborhood of plus infinity, then the term, the constant term plus the term in x, here the constant term is 0, you have 0 plus 2x. So the constant term plus the term in x will give the equation of the oblique asymptote. Okay, so I need the term in the constant term and the term in x. So I will go back to the choice of the second order here. In fact, why I choose to go to the second order, I need to calculate the constant term, the term in x, and then one additional term that will help me to know the position of the asymptote with respect to the curve. Okay, so if I go to the second order in the expansion in here, then the second order will be divided by t, so it will become a first order. So it's a first order in t. Since it's a first order in t, then it's an order of 1 over x, because t is equal to 1 over x. So that's enough. Always, if I go to 1 over x or 1 over x2, then it means that I have all the terms that will give the equation of the asymptote, the constant term and the term of order 1, and then I have one additional term in 1 over x or 1 over x2 or whatever that will give me the position. So I always need to go to the first order in t, or if the first order is 0, to the second order of t. So I need one non-zero order in t, not in 1 over t, in t, that will give me the first non-zero term in 1 over x to the power something, which will give me the position. Okay, so this is why I chose t squared, because it was divided by t. So to go to the first order, the first non-zero order in t, it will be I would be obliged to go to t squared for so when I divide by t, I will have t. So this is the oblique asymptote at plus infinity, and the limit of f of x minus 2x when x tends to plus infinity being equal to the limit of what's in here, so it's 0 minus, because it's 1 over plus infinity times minus, so it's 0 minus, being equal to 0 minus negative, then the curve of f is below the asymptote. Now, case number 2, if t goes to 0 minus, then x will be going to minus infinity. In this case, then g of t would be equal to 1 over t minus 1 over t times 1 minus t squared over 2 plus t squared epsilon of t, which will be equal to 1 over 2 t plus t epsilon of t, which means that f of x will be equal to 1 over 2x plus 1 over x epsilon of 1 over x. Then y equals to the constant term plus the term of first order in x, that they are not present in here, so they are equal to 0, then y equal to 0 is an asymptote to f at minus infinity. And since the limit of f of x when x tends to minus infinity, f of x minus 0 of course, being equal to the limit of 1 over 2x as x tends to minus infinity, plus of course 1 over x epsilon 1 over x, then this is being 0 minus negative, it means that the curve of f is below the asymptote y equals 0, of course at minus infinity. We move now to exercise 8, where we have almost the same work as in exercise 7. So first we have a function f of t being equal to the cubic root of 1 plus 3t minus 2t squared, and we need to calculate the finite expansion in the neighborhood of 0 to the second order of this function. So we can say that if we consider that this is u in here, then this is equal to 1, of course alpha is equal to, so it's of the form 1 plus u to the power 1 over 3, so alpha is equal to 1 over 3, so it's 1 plus 1 over 3 times 3t minus 2t squared plus half times 1 over 3 times alpha minus 1, so 1 over 3 minus 1 times 3t minus 2t squared to the power of 2 plus t squared epsilon of t, which will give, after calculation, 1 plus t minus 5 over 3 t squared plus t squared epsilon of t. Now for the second question, they are saying deduce that the curve of the function g has an oblique asymptote d in the neighborhood of plus or minus infinity. So g of x being equal to cubic root of x3 plus 3x2 minus 2x. So immediately I would say let t be equal to 1 over x, that goes to 0 when x tends to plus or minus infinity, and then we replace, then g of 1 over t is equal to cubic root of 1 over t cube plus 3 1 over t squared minus 2 over t, which will be equal to 1 over t cube to the power 1 over 3 times 1 plus 3t minus 2t squared to the power 1 over 3. So what's in here is f of t. So this is equal to 1 over t times 1 plus t minus 5 over 3 t squared epsilon of t. And this is of course equal to 1 over t plus 1 minus 5 over 3 t epsilon of t. And you see, in here they told us to go to the second order, but the idea was to arrive here to a first order in t, so it would be the first order non-zero order in 1 over x, sorry. Then g of x would be equal to x plus 1 minus 5 over 3x plus 1 over x epsilon of 1 over x. And from this we can conclude that the order 0 term and the order 1 term will give us the oblique asymptote. So it's the oblique asymptote in the neighborhood of plus infinity, plus or minus infinity. And since g of x minus x plus 1 is equal to minus 5 over 3x plus 1 over x epsilon of 1 over x, and if we look to this term in here, we can see that it's positive if x goes to minus infinity. Then the curve of f is above the asymptote, and it's negative if x goes to plus infinity, which means that the curve of f at plus infinity is below the asymptote. It's the same thing as if we calculate the limit of this theorem, which will be 0 plus or 0 minus, to understand if it's positive or negative, or we just look at the sign and we say it's positive or it's negative.